Hi, I'm going to make a video here on solving systems of differential equations. So find expressions for x and y in terms of t for the following system of differential equations. These are first order. So dx dt is equal to x minus y minus 3. dy by dx is x plus y plus 2, given that when t is 0, x is 1 and y is minus 2. Now, this is quite a long video, so hold your breath and see if you can follow it all the way through. Okay, so writing down the two differential equations, and we're going to label this one 1 and this one 2. And then from 1, we're going to make y the subject. So making y the subject, y will be equal to x minus dy by dt minus 3. So basically we've taken the y over here and taken the dx by dt over here. Right, now we're going to differentiate this one with respect to t. So the y will become dy by dt, the x will become dx dt. This minus the second derivative of this one of x, which is dx, d squared x over dt squared. And if you differentiate constant, you get nothing. We'll now substitute that for y and dy by dx into equation 2. We're using equation 2 because we used equation 1 for all of this. So, using a bit of colour here, dy by dt will become dx dt minus d squared x over dt squared. And then we're going to get the x, and then we're going to get the y, which is going to be x minus dx dt minus 3, and then we're going to add a 2. Right, writing that again here on the next slide. This is where we got to. Okay, this will give, if you rearrange it, a second order differential equation as d squared x dt squared minus 2 dx dt plus 2x is equal to 1. We're now going to solve this. So first of all, we're going to find the auxiliary equation. Okay, we're going to find a complementary function and a particular integral because it's not equal to 0. So using lambda, we're going to have lambda squared minus 2 lambda plus 2 is equal to 0. So you do need to know, before using this video, how to solve a second order differential equation. I have plenty here on the internet. Right, this needs to be solved using the formula. Okay, so 2 plus or minus square root of minus 2 squared minus 4 times 1 times 2 over 2 times 1 will give me 2 plus or minus minus 4 over 2. The square root of minus 4 becomes 2i, and then the 2's will cancel with the 2 at the bottom. We'll get 1 plus or minus I. So if we got a complex solution, then the complementary solution or complementary function will be of this e to the t, because the first bit here, and then the angle is given by the number in front of I, which in this case is 1. Makes life very easy. Okay, next thing we're going to do is find the particular integral. So we're going to try, because we've just got a constant term, we're just going to try the letter a as a constant, and we'll substitute that back into the differential equation, noting that if dx dt will be 0 and the second derivative will also be equal to 0. So we're going to have 0, substituting in, we're going to have into the differential equation, which we're writing down again, we're going to have 0 minus 2 times 0 plus 2a is equal to 1, a is equal to a half. Okay, we're getting there, just one more slide to go. Right, the general solution then is made up by the complementary function and the particular integral, so all you need to do is add them together. Complementary function, particular integral. Next, we're going to differentiate this. We're going to use the product rule to differentiate this. uv, so it will be e times the differential of this, so that will be differential sign is cos, and there's nothing in front of the angle, just 1, so it makes life easy for us. A cos t, and then the differential of cos will be b sine t, and the differential constant, we've got to do plus v du by dx, so plus v, which is that, times the differential of that, which in fact is itself, and the differential of the constant at the end is nothing. Right, so just putting that, well, we're just going to leave that in that. We're going to substitute that now into equation 3, which was that. So we're going to have that y is equal to e to the t. So we're going to all this, e to the t, a sine t plus b cos t. And I'll put the half down the end here. And then we're going to subtract all of this. And I'm going to keep that e to the t. So taking the e to the t out as a common factor. So changing the signs as we go through. So it's minus, plus, minus, and a minus again. Close up the bracket, and then we will need to put the minus 3 at the end. Okay, it looks quite horrendous, but actually quite nice things will happen now. The a sign will cancel out there. We've got a plus and a minus, and also the b cos. So we'll be left that y is equal to e to the t minus, bracket, minus a cos t plus b sine t, and then a half minus 3 will give me minus 5 over 2. So the next step is we've got to find these constants. So using the initial information, the boundary conditions or the initial conditions, t is 0, x is 1, y is minus 2. So using this one here that I've just highlighted, we're going to put the 1. Now the great thing is sine of 0 is actually 0, so we're just going to be left with b cos of 0, which is actually 1. So we're just going to be left with b plus a half, and then that will give me that b must be equal to a half. And then for the y1, we're going to put that y is minus 2, e to the 0 is 1. I forgot to mention that up there, sorry. E to the 0 is 1, and then we're going to have to get a minus a, because that's going to be 1, and we're going to get nothing from that, but we're still going to have the minus 5 over 2, and that will give me a is minus 1/2. Right, now substituting back into these two things and doing a little bit of factorization as well. So x will be minus a half e to the t sine t minus cos t plus a half. If you take that minus half in, it will give me that a is minus a half, and that will give me that b is plus a half here. And then similarly, we're going to substitute in this one as well. We're going to get y is equal to a half e to the t cos t plus sine t minus 5 over 2. Again, if you substitute back in, you'll see that you'll get a. It looks a bit confusing, but a is, it says minus a, so minus a is actually a half. So you substitute in, you get a half cos t, and then a half sine b. Okay, now that's really good. So, but what does that actually mean when we've actually solved it? So that's the answer. So I've got this GeoGebra app. Now the link to this I will put in the notes of this video. So I've got this GeoGebra app here. So we're solving those equations here. Those are the initial conditions. Okay, and if we click here, we will see the solution. Okay, so it starts here, okay, and what it does, it starts to curl away from that point. So I'm going to start animating time and zoom, but I would warn you not to zoom too much, or you might not be able to reset it. But I'm going to do zoom a little bit. So I'm going to start the time, okay, and then we'll see if we start zooming, you'll just see what's happening here to that function. Okay, so that's in this GeoGebra app. Okay, I think that's as far as I'm going to go, and it's going to let it go off on its own. Okay, you can see it keep coming back. So basically it's going to swirl away from that point there. So we can reset that and we can get back to the initial conditions. And then lower down here, you can actually see I've written down the solutions for you. Okay, I hope you've enjoyed this video. I'm sorry it's quite a long one, but I thought it's quite an interesting one to look up. And I thank you very much for watching. Like I say, the GeoGebra app will be in the notes of the video. You can just click on it, and also links to all my other videos as well. And I thank you very much for watching, and maybe I could ask you to consider subscribing to my channel. Thank you very much.